Chapter 8 focuses on proofs with sets. So we've actually been doing proofs with sets throughout the semester. You've seen some examples of those being written. You've had to write some yourself. But now that we've had some time to discuss these formal proof techniques, we want to go back and think about our proof with sets from this more formal perspective. So we're going to go through 3 different topics here. So how do we prove that a specific element is an element of a set? So if you want to reference in the book, that's section 8.1. We'll also talk about how to show that a set is a subset of another subset. That's in section 8.2. And finally, we'll talk about how to show that 2 sets are equal. That's in section 8.3. So let's start out with showing that A is an element of some set A. This depends on how we actually define our A, right? So the way that we prove this depends on how we define A. But usually it's going to be given in some sort of set builder notation, or you can rewrite that in a set builder notation. So if I think about A as the set of X that satisfy P of X, then to show that A is in that set, little a, I just need to show that little a satisfies P of X. So I just need to show P of A, right? So let's actually go ahead and do that in an example here. So how do I show, whoops, I got a wrong symbol there, let's fix that. How do I show that 28 is an element of this set? Well, I just need to show that 28 satisfies the condition of this set. So we want to show here that 28 is an element of n, and 7 divides 28. That's what I want to show. So I can say we know by definition of the natural numbers that 28 is in n. And to show that 7 divides 28, I need to show that 28 can be written as something times 7. So 28 is 4 times 7. So 7 divides 28. Thus, 28 is in the set. So I'm just showing exactly why, or explaining exactly why it satisfies the conditions of that set. Now, if my set was defined with a little bit more information, so I'm taking now the set of X in S, such that P of X is true, then really I want to think about this as the set where I have X, where X is in S, and P of X is true. I need to show both that my A, the thing I'm trying to show is in this set, that A is in S, because that satisfies that first rule, and that A satisfies my P of X, so I need to show P of A for whatever that rule P is. Okay, so let's look at an example of this. So I'm asked to show if 4 divides X, then X is an element of this set. So this is actually a conditional statement, but it's got that set containment or that set element inside that. So I'm going to start off with my conditional proof. So I'm going to assume my if. I'll assume 4 divides X. And then I'm going to exit the proof for a second, and I just want to think about what I want to show. So I wouldn't write this in my formal proof write-up, but it's helpful to consider. So I want to show that X is an element of the set of X in Z. Probably shouldn't use X twice, so let's go ahead and just change that X here to a different letter, just so it's not repetitive. Fix our notation a little bit. So my X is going to be in, I want to show that X is in the set of Y in Z such that 2 divides Y. So to show it's an element of this set, I need to show that X is in Z and 2 divides X. So this is where, here is where I'm using the definition that we just learned. And overall, this is a biconditional proof. So I know where I'm heading. So assume 4 divides x, then by definition of divides, x is equal to 4 times k, where k is in z. I want to try to show that x is an integer and that 2 divides x. So I'll say that this is equal to 2 times 2k, where 2k is in z. So then I can say since k is in z, 4k is in z, so x is in z, and x is equal to 2n for some n in z, in particular n equals 2k. So 2 divides x. Thus, since I satisfied those two conditions, I can say x is in this set, the set of y and z, such that 2 divides y. Right, so really, what did I show in other words? 4 divides x, right? If x is a multiple of 4, then 2 divides it, it's even. So we just use sort of a weird step proof to show that any multiple of 4 is also even. Next up, we want to talk about how to prove that some set A is a subset of another set B. So what does it mean that A is a subset of B? We can think of this as saying if A is an element of A, then A is an element of B. Right, so we want to think of this as every element of A is in B. So if we have something in A, then it's in B. Or, alternatively, for all A in A is in B. So we've seen that these two statements are logically equivalent here. Use my logically equivalent symbol. Okay, but now that I've rewritten this expression as an if-then, right, I'm trying to show A is in A implies A is in B. We know how to prove that because we know how to prove conditionals. So I'm just going to assume A is in A, and then show, explain, lead to why A has to be in B. So that's like doing a direct proof of that if-then. I could also do a contrapositive proof of that if-then. So instead, I could assume that A is not in B and go ahead and show why A can't be in A. So because this is just an if-then statement, I can just either do that direct proof or that contrapositive proof. So we just have to make sure we're always thinking about this subset as an if-then. Let's look at an example here of proving that A is a subset of B. So I want to prove that the set of x and z, such that 2 divides x, intersect the set in x and z, where 9 divides x, is contained in the set of x and z, where 6 divides x. Okay, so again, I'm going to call this huge set here A, and this set B. So I can put that in my proof, that A is equal to this set. I'm just going to be lazy and not actually write it off. And B equal to this set. We don't have to do that, but it might save us writing so much later on. So then this subset is really just an if-then. So I'm going to assume that an element, let's call it A, is in that set A. Then since A is an intersection, I can say that A has to either be in the first set, sorry, not either, but it's an intersection, so and. So X is in that, and A is in the second thing. So both A is in the set of multiples of 2, and A is in the set of multiples of 9. But in order to be in that set, that means it satisfies the relationship of that set. So we know that 2 divides A and 9 divides A. So A can be written as 2 times K, and A can be written as 9 times M, where K and M are in Z. And now I'm trying to show that it can be written as 6 times something. And I recognize that 6 is 2 times 3. So if I can get the 2 from here and the 3 from here, then I should be able to kind of put it together. But right now, those are separate statements. So let's see how we can build that up. Since I know that A is equal to 2K, that means that A is even. And A is equal to 9 times M. So if it's even, then it has to be written as an even number in the product. So M can't be odd, because if M was odd, you have an odd times an odd, which wouldn't give you an even. So we get that M is even. Thus, we can say that M is equal to 2 times, I need a new letter. Let's use N. I haven't used that one yet. So now I get A is equal to 9 times 2 times N, which is 6 times 3N. So A divides 6. Just kidding, other way around. 6 divides A. Thus, A is in the set. Oh, let me throw in one more thing. I had to say it's an integer. And A is an integer. I'll put that up here as well, just so we are sure. Thus, it's in the set of integers such that 6 divides X. So what did I do? I started with something in A. I showed it's in B. Thus, we can conclude that because I started with an arbitrary element in A and got the fact that it was in B, that every element in A is also in B, therefore A is a subset of B. So I definitely encourage you to go back, look through this proof, make sure you can see where all the lines come from, and think about this as proving an if-then statement. Okay, let's do one more of these. So if A and B are sets, then the power set of A union the power set of B is contained in the power set of A union B. So I encourage you to take a second, think about this, convince yourself if it's true and why it's true, and that'll help us sort of get ready to do the proof. So when you're ready, come back and we can kind of talk through it. Okay, so let's look at that. So I know, right, it's of the form of an if-then. So I should assume the if that A and B are sets. And I know I'm trying to prove that we have this subset. That subset itself is another if-then. So then I should also assume I have some element, let's call it X. I'm going to use a capital X because it's a set, because the elements of power sets are sets. So assume X is an element of the power set of A union the power set of B. Okay, and what I want to show is that X is an element of the power set of A union B. Well, what does it mean that X is an element of the power set of A? That means that X is either an element of the power set of A, or X is an element of the power set of B, because we have that union. So because I have that or, we could do cases. So let's consider 2 cases. I could say if for my different cases, but I'm just going to be more explicit here and say case 1 and case 2. So case 1, when X is an element of the power set of A. By definition, that means X is a subset of A, because the power set of A has the subsets of A as its elements. But if it's a subset of A, since now we can prove this as a lemma, or you can just believe me, A is a subset of A union B. Right, everything in A is also in A union B by definition of the union. Then that means that X is a subset of A union B. So there's certainly a little bit of stuff to prove, and I encourage you to prove these as lemmas. So for any set C, C is a subset of C union anything else. So for all C and for all D, C is always a subset of C union. I drew intersect. Let me fix that. And lemma 2, we have a transitivity property. If A is a subset of B and B is a subset of C, then A is a subset of C. So I'll leave those for you as exercises. Perhaps you'll see those on your homework. All right, so I used all that. I have that X is a subset of A intersect B, so I can conclude, because it's a subset, that it's an element of that power set, which is what I wanted to show. Case 2 is going to be very similar. When X is an element of the power set of B, then X is a subset of B, and B is also a subset of A union B. So X is a subset of A union B, again using my two lemmas. Thus, X is an element of the power set of A union B. So again, I encourage you to go back, read through these two proofs. I'm proving an if-then, and then within that if-then, I'm proving a set containment, which itself is really an if-then. So my first assumption here comes from my original if-then. My second assumption comes from the if-then of my set containment. So again, see if you can kind of break down that proof structure and think about where everything comes from. Here's a similar question that I want you to try. So suppose A and B are sets. I want you to show if the power set of A is a subset of the power set of B, then A is a subset of B. So go ahead, think about that, and we'll discuss it in class. Finally, let's talk about how to prove A equals B. So what's the technique we're going to use? I think we've talked about this a little bit before, but whenever we want to show two subsets are equal to each other, what we do is we show the first is a subset of the second, and the second is a subset of the first. So it's really just two separate proofs of the form that we've done before. So again, for showing this, we'll show if X is in A, then X is in B. And to show the other one, we show if X is in B, then X is in A. So let's think about why this is true, right? Why is that what we want to do? Well, we know that A equals B when A and B have the same elements. So what we're saying is if they have the same elements, then every element in A is also in B, and every element in B is also in A. And as long as both of those two things are true, then we can't have anything extra in our set. So they must have exactly the same elements. So I'm just showing that every element in A is also in B. If it's in A, then it's in B. And every element of B is also in A. And therefore they have to be equal. So let's do one example of proving two sets are equal. So I've got A, B, and C here are sets, and C is not the empty set. And I want to prove that if A equals B cross C, then A equals B. So if for any set C, we know that A cross C equals B cross C, then A has to equal B, right? But this works even if I only know it's true for one specific C. So I can't just be like, oh, well, if it's true for all the C's, right? I don't know it's true for all C. I just know there's one C that this works. And I want to say that if for some C, which I have no idea what it is, A cross C equals B cross C, then A has to equal B. So let's think about how we would actually show this, right? It's written as an if-then. So I'm going to assume the if A cross C equals B cross C. And then what do I want to show? I want to show A equals B and B equals A. Sorry, I want to show A equals B. But in order to show that, I have to show A is a subset of B and B is a subset of A. And each of these are their own if-then proofs. So maybe we should tell the reader that that's our plan. So to show A equals B, we will show A is a subset of B and B is a subset of A. So let's say first, I'm going to do this guy first. To show that, I'm going to assume some element is in A. Then, now I know A cross C is equal to B cross C, so I have to use that information to tell me something. So I also know that C is not empty. So perhaps we should have assumed those things up here. So assume A, B, and C are sets, and C is not the empty set. So since C is not the empty set, then since C is not the empty set, there exists some element C in C. So I have something in A and I have something in C. So putting those together, the pair must be an A cross C. Because that pair is an A cross C, and A cross C is equal to B cross C, then A cross C is also in B cross C. But the only way that A cross C can be in B cross C is if that A lives in the set B. So I started with an arbitrary element here in A. I ended up being able to conclude that that element was in B. So I get that A is a subset of B. Now similarly, I can go back the other way, assume B is in B, then there exists some C in C, so we get BC in BC, which is equal to AC, so BC is an element of A cross C, thus B is in A. So I started with an arbitrary element in B, I concluded it was in A, thus B is a subset of A, and then finally, since A is a subset of B and B is a subset of A, we can conclude that A is equal to B. All right, so go back, take a couple seconds, look over this proof, make sure it kind of makes sense. Again, I was trying to show a set equality here. So I started with an element in the first set, explained why it had to be in the second using the information I was given, and then I started with it being in the second and explained why it had to be in the first. But that was part of my conditional statement. So at the beginning, I had to assume the if bits of my conditional. So I did that if part for my conditional, and then to show that equality, I split it up into two subsets, and each of those subsets were its own if-then proof, so they each came with their own assumption. So again, see if you can track down where all the assumptions came from and think about that from a proof structure perspective. Okay, finally, one more discussion question exercise for you all. So I want you to go through, and in the book, there's two different proofs of the fact that A cross B intersect C is equal to A cross B intersect A cross C. So I want you to read through those two different techniques. One is more wordy, where they kind of go through and explain it just like the proof we just did. And the other one is going to allow us to sort of use logical equivalences by breaking down the logic of our different symbols, of our and symbol, of our or symbols, using some intersections, some De Morgan's laws, and those sorts of things. So I want you to go through and read those proofs and to see which one you prefer. And we'll talk about those in class and see if there's anybody has any questions on those.